Homework problem that I need to talk about. I forgot to talk about this at the time. But when we do skeleton, the setup that I showed you works for acidic and neutral solutions. And so if there's H plus present, or if there's no H plus and there's no H minus, then that works. However, if we're in basic solutions, then the dominant species is hydroxide. You know, all the bases produce hydroxide. Strong bases hydrolyze water to produce hydroxide. Weak bases hydrolyze water to produce hydroxide. It's the difference between a strong base and a weak base is the amount of hydroxide that you produce. And so in basic solutions we have hydroxide, but how do we balance H's? In skeleton redox we balance H's by adding H+. H+ is acid, and if we have H+ and hydroxide together, they're not compatible. And what's going to happen is the H+ and the hydroxide will react to form water. And so we have to do one extra step when we do skeleton redox in basic solutions. And so this is what I'm talking about here, one extra step. And so I had a question this morning on one of the homework problems, so I'll just do that one. Just right here. And that was this MnO2 solid. What's that called? MnO2?
Manganese dioxide.
Yeah, manganese dioxide is one name for this. Another name for this is manganese. This is a metal and a nonmetal, so usually with the nonmetals we use the prefixes like carbon dioxide. You know, carbon's a nonmetal, oxygen's a nonmetal. But typically when we have a metal and a nonmetal, we don't specify how many. You know, like iron 3 oxide.
Like manganese 2 dioxide?
Yeah, except it's not manganese 2, it's manganese 4. 4. So this is manganese 4 oxide. That's the way we name it, but a lot of people call this manganese dioxide using the molecular nomenclature system. But the proper name for this is manganese 4 oxide. And this ClO3 minus, what's that called? Chlorate. And so what happens when you mix these together? In skeleton redox, we don't have to think what happens when you mix these together because they tell us what the major products are for this. And the major products for this that they found were this, MnO4 minus and Cl minus. MnO4 minus is called permanganate, and Cl minus is this chloride. And so what happened here? Well, this is manganese in the +4 oxidation state. That's why we called it manganese Roman numeral 4 oxide. From manganese, if manganese is +4, then we need 2 oxides to balance out the charge. And so we went from manganese 4 to, what's the oxidation state of manganese and permanganate? +7. So we went from manganese 4 to manganese +7 and lost electrons. In fact, it lost 3 electrons. And so losing electrons, that means it was oxidized. Oil rig. You heard of oil rig? Oil is oxidation is lost. So manganese was oxidized. It went from +4 to +7. Who did the oxidizing? Who did the oxidizing? It must be chlorate must have done the oxidizing. So chlorate went from, what's chlorine's oxidation state here? +5 to -1. So chlorine and chlorate did the oxidizing. So in the process, chlorate was reduced. Reduction is gain. So the oxidizing agent will gain electrons. We don't have to analyze skeleton redox to this extent, but basically we oxidize the manganese 4 oxide using chlorate. In skeleton redox, what we do is we break it up into half reactions. So the first half reaction is MnO2 goes to MnO4 minus. The second half reaction is ClO3 minus goes to Cl minus. Sometimes these half reactions are common, and we can just copy them off a chart. And so let's see if our chart has these particular half reactions here, so I can save myself some work. So the redox chart, we don't memorize the redox chart, but then again, we don't completely ignore the redox chart. You know, I don't review the redox chart daily, but I would review it, you know, periodically. Like maybe every week I'd review it, or twice a week or something I'd review it. And how would I review it? Well, I just review it just by reading it. You know? That's an initial step. So for example, fluorine is the, what? Strongest oxidizer. And so I just read it, fluorine, and then ozone, and then there's this weird disulfate thing that turned out to be a peroxide. I talked about this, right? And then hydrogen peroxide, and then permanganate. Well, there's permanganate over here. And so I need permanganate and MnO2. But when I look at this, I have permanganate and Mn2+, not MnO2. If I had permanganate and MnO2, I'd just copy it. You know, I might have to reverse it because permanganate here is a reactant, permanganate there is a product, so I just flip the reaction over. Does that make sense? But unfortunately, it didn't pan out for us. So we'll just keep going down. After permanganate comes, not lead-2 oxide, lead-4 oxide, followed by, what's that? Chlorine, followed by dichromate, followed by manganese 4 oxide. Well, manganese 4 oxide, I have manganese 4 oxide right here. So this is manganese 4 oxide goes to manganese 2+, but we need manganese 4 oxide going to permanganate. Unfortunately, this isn't going to work for us either because it's not quite what we're looking for. So we may end up having to do the work. And then we go to oxygen and then iodate. Iodate, but we have chlorate here. They're in the same family, iodate and chlorate. So maybe we could just use this, except instead of writing chlorine, instead of writing iodine, we substitute that with chlorine here. So we have chlorate. But if we look at this iodate, it goes to iodine. Ours goes to not chlorine, but it goes to chloride, so we can't use that either. Maybe there is chlorate in here, so we'll just keep going down the list. Iodate, and then bromine, and then nitrate. Silver ions, this is interesting. Silver ions are actually a pretty good oxidizer. It's a +1, but it's a +1, but maybe what's really driving this is silver metal. Silver metal is quite stable. Iron 3 also. Iron 3 is an excellent oxidizer as well, surprisingly. This oxygen, well, we have a better oxygen up here, so we're going to skip this oxygen. And then iodine, and then copper 2, and then sulfate. Sulfate's kind of surprising because it's not that strong, you know? Because you'd expect it to be stronger. What's the oxidation state of sulfur and sulfate? +6. So I'd expect it to be stronger being at +6, but it isn't so strong. And then tin, it's 4+. This is pretty high charge here. And then sulfur. Sulfur is quite a bit weaker than oxygen. Quite a bit weaker. And oxygen goes on to form water, whereas sulfur goes on to form oxygen goes on to form water, and sulfur goes on to form hydrogen sulfide. And then when you start reading this, like a lot of people will never read this. But when you start reading this, you'll start to know some patterns, or notice some patterns. One of the patterns that you notice is this. The halogens are all good oxidizers. You have fluorine, and then chlorine, and then bromine, and then iodine. Iodine being the weakest. Fluorine's at the top. The fluorine, chlorine, bromine, iodine. Well, that makes sense, right? Fluorine's the most electronegative. You also notice some other patterns. Have you noticed like this? I kind of ignored these. Like ozone plus 2 H pluses. Hydrogen peroxide plus 2 H pluses. Permanganate plus H plus. Have you noticed these H pluses all over here? What's going on with H plus? Well, when we look at the oxidation state, let's pick permanganate and H plus here. If we put permanganate and H plus, we go from +1 to, what's the oxidation state of hydrogen and water? Not -1. Oxygen is -2. Hydrogen is +1. So it wasn't the hydrogen ions picking up the electron. What was picking up the electron was permanganate. Permanganate was picking up the electrons in this, 5 electrons. In fact, we're going from +7 over here in permanganate to +2. So to go from +7 to +2, we need to gain 5 electrons. But what's going on with the H pluses? What's going on with the H pluses is this. If we didn't have any H, could we form water? No, we can't form water. So if we lost the water, what would we, not the water, but the hydrogen, and we'll lose the water, excuse me, because of that. If we didn't have hydrogen here, what would we have formed? Not O2. What's the oxidation state of oxygen in water? It would be -2, right? Oxide. And so if we didn't have the hydrogens, we'd be left with oxide. Is oxide very stable in water? Can oxide exist in water? What's the most powerful? Oxide, you know, is a powerful what? It's a powerful base. And it's too powerful to exist in water. And so what's going to happen here is we're going to form something very unstable. If we don't have hydrogens, H pluses, then we cannot form water. If we cannot form water, we're going to form oxide. Oxide's a terribly reactive base. And so take a look here. We're going to be left with 4 oxides, but in order to stabilize that, how many hydrogens are we going to need in permanganate? In other words, if we have 4 oxygens, how many hydrogens do we need to form waters? 8. If we have 2 oxygens, how many hydrogens do we need? 4. If we have 7 oxygens, how many hydrogens do we need? 14. Do you see the pattern here? The pattern in general works unless you form other things, like here. You know, here we have 3 oxygens, but we form other things. We form O2, which doesn't need any hydrogens, and we form 1 oxide, which needs hydrogens. So we only ended up having 2 H pluses. But for the most part, all these are correct. Like iodate. Iodate needs how many hydrogens? 12. We would form 6 waters. So that's because it's 2 iodates. That's why. All right, so those are some patterns that we can see. And so periodically, like at least once a week or more, I'll just read all the entries. You know, from the strongest oxidizer to the weakest, which would be lithium ion, and then the basic ones too. The basic ones, you know, for example, can we have H plus in basic solution? No, this is strong acid. So if the solution's basic, then we have lots of hydroxide. So we can't have that. And so some of these are for basic solution. That's why we have this other chart here. If we have basic solution, then we're going to have hydroxide present rather than H plus. So we see the hydroxides over here. It doesn't matter which side. This chart is on Canvas. I put it here. I just, for some reason, I didn't publish it. I had it up there. Sorry, it was supposed to be published last week, but it's here now. And so we have ozone again, and then this is hypochlorite, bleach, oxygen again, but under basic solution. So ozone under basic solution, oxygen under basic solution, water, which will be under basic. Okay, then we look at the reducers, lithium, etc. This is kind of the activity series. You have the alkali metals, which are very reactive, lithium, potassium, sodium, and the alkaline earths, calcium, magnesium, and then aluminum. Zinc is quite reactive, iron, etc. The metals are electron rich. H2S is electron rich, tin 2, sulfur dioxide, copper, metal, etc. So we read these. You go through, fluoride being the worst here. So unfortunately these weren't on the chart. If these were on the chart, I'd just copy it. And so that means we have to go ahead and balance these. So the manganese is already balanced. So we don't have to do anything here. Then we have 2 oxygens here, 4 oxygens here. The oxygens we balance by adding water, so I'll add 2 waters over here, and then this is going to give me 2 times 2 is 4 hydrogens here, and then no hydrogens here. And so I need to add 4 H pluses. Well, if this is under basic solution, then I'm not supposed to add H pluses, that's acid, right? But I'm going to balance everything exactly the same as acidic solution and change it at the end. Some people change it here. I'm not going to change it here because it's more steps. Okay, then we look at the charge, 0 and 0. -1 plus 4 is plus 3, 0. So I need 3 electrons over on this side, and that should balance things out. So I'm going to take my manganese 4 oxide, solid, plus 2 waters, yield permanganate, plus 4H plus, plus 3 electrons. So we went from manganese plus 4 to manganese plus 7, so we got to lose 3 electrons. So this is showing loss of 3 electrons here. Okay, and then we go over to the chlorines are balanced over here. 3 oxygens, 0 oxygens, so we're going to add 3 waters to the right. And then that's going to give us 6 hydrogens on the right and 0 hydrogens on the left. So we'll add 6 H pluses. And then we'll add the charge. -1 plus 6 gives me plus 5. And then over here, -1 and 0 gives me -1. And so how do I balance the charge here? It's plus 5 on the left, -1 on the right. So how many electrons do I add into which side? Okay, I have to add 6 electrons on the left. That's going to give me a -6. -6 plus 5 is -1. Now they're balanced. And so this half reaction is going to be ClO3 minus plus 6H plus 6 electrons. This is going to go to chloride plus 3 H2O. And then I'm just going to add them up. So this first produces 3 electrons. The second consumes 6 electrons. So I'm going to multiply the first one by 2. So I'm going to get 2 MnO2 solids plus 4 H2O liquid. Okay, then add these chlorate plus 6H plus 6 electrons. So that's all the reactants. And then this is going to go to the products, which will be 2 permanganates plus 8H plus 6 electrons plus chloride plus 3 H2O. All right, then I'm going to go ahead and try to simplify this as much as possible. So I have 3 waters here. I'm going to cancel 3 of the 4. That's going to leave me with 1 water there. And then I have 6 H pluses here. I'm going to cancel 6 of the 8, and that's going to leave me with 2 H pluses left over here. All right, now I have 2 H pluses. It doesn't matter where the H plus occurs. It occurs on the left side or the right side. We have to get rid of it. Because if we have base is hydroxide. And so the hydroxide is going to neutralize the H plus. So what I need to do is I need to add 2 hydroxides to both sides of the equation. I have to add it to both sides because it'll screw up the atom balance if I don't, and the charge balance. So I'll just add it to both sides. On the right side, I'm going to have 2 H pluses plus 2 hydroxides. That's going to make 2 waters. So go ahead and write that over here.
No, no, right side. Yeah, let me take a picture.
Okay. So I'm going to have 2MnO2 solid plus H2O plus ClO3 minus plus 2 hydroxides. Okay, the 6 electrons also cancel. The electrons must cancel. Okay, this is going to produce 2 permanganates plus, now the 2 H pluses and 2 OH minuses will make 2 H2O liquids plus chloride. All right, see if we can simplify it further. Yeah, the H2O I can cancel from here, and that leaves me with 1 H2O on that side. And so overall, the reaction is going to be 2 MnO2 solid plus ClO3 minus plus 2 hydroxides yields 2 MnO4 minus plus H2O liquid plus Cl minus. I wasn't supposed to erase those half reactions, unfortunately. But it's all right. Remember the conjugate relationship? MnO2 was our oxidizer or reducer? MnO2. Was that our oxidizer or reducer? Did it lose electrons? Look at the half reaction. Are the electrons on the left side or the right side of that reaction? Yeah. So this was our reducing agent. Chlorate was what? Or oxidizing agent. And then the conjugates. That means chloride, which is the conjugate of chlorate, will be the reducing agent. And permanganate, which is the conjugate of MnO2, will be the oxidizing agent. So in the analysis here is for all skeleton redox, driving force is present. So what that means is that if there wasn't a driving force, then they would have never analyzed this for the products. The products were permanganate and chloride. And so there's got to be a driving force present. And so that means we're going from stronger to weaker. And so we're going from a stronger RA, stronger OA, to weaker OA, weaker RA. And so this would be the analysis. We know that there's a driving force present. We just have to label these things. And so what this tells us is it tells us the relative strength. So which is a stronger OA? Chlorate or permanganate? Chlorate is a stronger OA. And so in experiment 18, you're supposed to make a table. The table that they had was the strongest oxidizer on the bottom left. I don't like it. I like the strongest oxidizer on the top left, so it mimics this chart. And so if that's the case, what we do is we position chlorate, above chlorate above permanganate. So what this means is that chlorate is a stronger oxidizer than permanganate. And then we look at the conjugates. The conjugate of chlorate is chloride. And the conjugate of permanganate in this reaction is MnO2. And so as far as reducing agents go, I like them to be strongest at the bottom right, like on that chart. And so what that means is that manganese 4 oxide is a stronger reducer than chloride. And so this tells us the relative position here. So if we go back to this chart, let's take a look at here. Iodate was here. What do you expect to be a stronger oxidizer? Iodate or chlorate? So for example, what's a better oxidizer? Chlorine or iodine? Chlorine. So I would expect iodate to be weaker than chlorate. But so chlorate's above here, but we know here's permanganate. If this is permanganate, then where's chlorate? Chlorate's above this. So chlorate is in this range here. Do you see that? Chlorate is up in this range, above permanganate. And so the pre-lab for experiment 18 involves doing these. You know, if you know reaction occurs, there's a driving force, then we can rank the oxidizers. If we can rank the oxidizers, then we'll have a little chart. And then we can also rank the reducers because they're conjugates one another. Uh-huh.
Sorry if you went over and I just didn't catch it, but how do we know that this is a basic solution? Like, how do we know that we need to add that?
Okay, how do you know it's a basic solution? Because they got to tell you.
Oh.
They got to say this is in basic solution, and then you'll do that. Otherwise, if they don't tell you if it's in basic solution, then you assume it's in acidic or neutral. Neutral, you don't have to do anything because of no H+. So this was, I think, problem number 5 or something, 39. I think this is like number 39 something in chapter 5. Chapter 5? Yeah. All right, but that's not what we're doing today. What we're doing today is we're going to try to use the chart to predict the products of the reaction. Okay. The original experiment is you look and see, do you observe a reaction or no reaction? If you observe a reaction, then that must mean there's a driving force, and then you can play around and rank things. But for this lab, I'm not going to follow that procedure. What we're going to do is we're just going to predict all the reactions and see if our observations agree with our predictions. And so I'm going to quickly go through the reactions here. I was going to have you guys do it, but we don't have enough time since I got behind schedule here. So I'll just do the reactions, most of them.
Are we going to finish experiment 17 or no?
Where did we leave off on 17?
I think we were on number 9.
Number 9, which was, what reaction was that?
Sulfuric acid and
Sulfuric acid and ammonium acetate. There's no sulfuric acid and ammonium acetate, I think. Did we do iron 3 nitrate and ammonia?
Yeah. That's the one we did off on.
Okay. And so we have ammonium acetate and sulfuric acid. That one? Oh, I guess we do have it. Sulfuric acid and ammonium acetate? Ammonium acetate and sodium hydroxide? Okay. Those ones, I think I might have skipped those ones. Let's see. Those are demos. So I'm going to skip those for right now. We'll come back to those. I can demo those at another time. So this is not quite complete. I need to make sure we have enough time to finish today's lab. And so let me skip those for right now. We're going to look at, you guys are actually going to do these reactions. I'm not going to do them, so I don't need my goggles right now. We're just going to do this first by prediction here. And so let's go to experiment 18. I'm going to look at page 18. Let's see. I'm going to look at page 18.5. And so we're going to take copper metal and do some reactions. The first reaction is, okay, I'm going to omit the ones that require lead. So for example, it says 0.1 molar lead-2 sulfate. That's a typo because lead-2 sulfate is insoluble. Sulfates, for the most part, are soluble except for silver, lead, mercury, calcium, strontium, barium. So that's what's supposed to be lead-2 nitrate. But we're going to omit lead, all. That's steps. So anything involving lead, we're just going to skip it. Lead is a heavy metal. I don't want anybody going for EDTA therapy in this class. So, including me. I don't want EDTA therapy. Yeah, just cross out all the lead ones. We're not going to do the lead solutions or the lead metal.
What was that Santa Barbara's Hall of Fame again?
The Wall of Horrors.
Yeah, Wall of Horrors. What were they using?
Hydrofluoric acid, stuff like that. Yeah. But the lead doesn't really cause any visible damage. It's just it's bad for your brain. What are some other heavy metals? Silver is also a heavy metal. So we have to be careful with silver. I'm not going to omit silver though. I think maybe it's less of a problem. Plus, you can see easily if you've spilt silver salts on you. Do you know how you can tell? Silver stains everything black. So if you spill some on your paper, it stains it black. If you spill some on your skin, it stains it black. And you definitely don't want it in your eyes because it'll stain them black too. The problem is I had this student, this is in Chem 4, and they spilt a whole bunch of silver nitrate all over their hands. So they were at the sink washing their hands, I think for like 20 minutes. But they couldn't wash off the silver nitrate stains. And this student had an important job interview after lab, and so a bit, a bit frantic. But unfortunately, you can't wash it off. You just have to wait for the skin to shed off. Because what happens is silver ions are actually a pretty good oxidizer. So silver ions will oxidize paper. When it oxidizes paper, what does it form? Silver metal. So it's going to form a small precipitate of silver. But initially, when we precipitate out silver metal, they start off as tiny crystals. And tiny crystals of silver, do you know what color they are? Black. As the crystals grow bigger and bigger, then they'll have their lustrous silver metallic color. But initially, tiny crystals, black. And that's what you see. When they stain your fingers black, those are tiny silver crystals precipitating out in your skin. And they're in the cells, so you can't wash them off. So it's difficult. Well, lots of people wear silver jewelry, so I think that's a little less hazardous than lead. So we're going to keep it. So watch out for the silver nitrate. But what we're going to do is we're going to skip the lead and we're going to take copper and react it with zinc. And so the first reaction we're going to do is we're going to take a square of copper metal, which is located in the counter over there by the white bucket. And then we're going to add some zinc nitrate to that, or zinc sulfate. Was it zinc sulfate? No, zinc nitrate. So we're going to add some zinc nitrate solution. The zinc nitrate solution is in one of these hoods over there. All the solutions are in the hoods. And so look for the zinc nitrate. And let's see what it forms. All right, this looks like what type of reaction? This looks like a single replacement reaction. In a single replacement reaction, it's A plus BX forms what? AX plus B. So what would copper, it would be copper 1 nitrate or copper 2 nitrate? Copper 2 nitrate. And zinc metal. And so in a single replacement, copper is the reducer, zinc ion is the oxidizer, and nitrate is the spectator. Does that seem to kind of be in line with what we observe on the chart here? So zinc ion is an oxidizer. And what else do we have? Well, what else we have is we have nitrate and water. So zinc, the strongest oxidizer out of those three, zinc ion versus nitrate versus water. Well, I would think zinc ion would be better than water. Water is really, really weak. But what about nitrate? Nitrate is, do you see nitrate's much stronger? So, in a sense, this reaction doesn't make sense, because if I had a competition between zinc ion and nitrate, who's more powerful? Nitrate is significantly more powerful. Do you see that? And so it does not make sense, this single replacement reaction. Because nitrate shouldn't be a spectator, nitrate should react. However, nitrate needs what? If I have three oxygens here, this is a bit tricky because one of the oxygens stays on. So normally if I have three oxygens, I'm going to need 6 H pluses, but here I only have 4 H pluses. I only have 4 H pluses because two of the oxygens will come off, one stays on. And so I'm only going to make 2 waters. And so if I have nitrate here and I have no acid, then can I form water? In other words, I need H plus in order to form H2O. If I don't have H plus, then I'm going to form what? Oxide. Is oxide very stable? No, oxide's a very powerful base. And so, in this case, this is my analogy. My analogy is, let's say you're baking some cookies or something, and the recipe calls for 4 cups of flour, that would be the H plus, and 1 cup of sugar. If you only had 1 cup of sugar and no flour, could you make the cookies? No. And so what that's going to do is it's going to drop nitrate's rank way down here. It'd still be an oxidizer, but not nearly as powerful, because we're making an unstable product, oxide, instead of water. And so what that means is there any acid? Do you see any acid here? No, this is neutral. Since there's no acid, then nitrate is not going to have the same rank here. In fact, if there's no H plus, then we kind of ignore nitrate because it's going to be so much weaker. Does that make sense? And so it turns out that single replacement is okay here because nitrate's missing the H plus, and therefore it's not going to react. It's just going to be a spectator, and therefore zinc will be the strongest oxidizer. But if we look at this, we're going to use the activity series. The activity series is here on the right, the bottom right. The most active element is lithium, and then we're going to compare copper and zinc. So zinc is up here, and then copper is here at the top. And so that means zinc is more active than copper. Lithium is the most active. And so what we're doing is we're going from less active copper to more active zinc. Is that the direction we want to go? Do we want to go from less active to more active? No. Because what we're doing is we're going to less active means more stable. What we're doing is we're going from more stable to less stable. That's not the direction we want to go. Oh, actually, more stable to less stable, yeah. In other words, this is a weaker reducing agent. This is a stronger reducing agent. And the driving force is going to be backwards. And therefore, forwards, we expect no reaction. And so when you do this, we expect to see no reaction here. Activity, in the activity series is the strength of a reducing agent. The most active is lithium, and that's the strongest reducing agent on the chart. Okay, that's copper and zinc nitrate. Zinc only has 1 charge, 2 plus. Now we're doing copper and silver nitrate. So here you want to be careful with the silver nitrate. Okay, it looks like we have 2 pretty good oxidizers. Silver ions and nitrate. And in fact, it looks like nitrate is a stronger oxidizer than silver ions, correct? Based on the chart. But we're missing something in this reaction. What are we missing in this reaction? H plus, and that means nitrate's going to drop down in rank. That's going to give silver ions the strongest. So it looks like single replacement will work here. I'm going to use single replacement because it's faster than the chart method. The chart method, we don't have to analyze it like this. The chart method should work regardless of our analysis or not. And so what will we form here? Copper plus silver nitrate is going to yield copper 2 nitrate and silver metal. Okay, now I don't think you need the chart. Which one do you think is more stable, silver metal or copper metal? Like quarters versus pennies. Which one will last longer? Quarters versus pennies. Or do they last the same? You think quarters last longer? Yeah. The pennies will start to tarnish before the quarters will, usually. And silver jewelry versus copper jewelry. You know, which one's going to last longer? Probably silver, right? And so we probably don't even need the chart for this. We know that copper is less active, or more active. Actually, copper is more active. More active means more reactive. In other words, it's a stronger reducing agent. Stronger reducing agent's easier to oxidize. And silver is less active. Less active means it's a weaker reducing agent, which is harder to oxidize. It's harder to oxidize silver than copper. Or we can just look it up on the chart. We can look it up on the chart and we'll see that silver is more stable, less active than copper. Copper is more active. It's closer to lithium. And so we expect a reaction here. And so we have driving force. And so what we're going to do with this one is we're going to write the CE, the IE, and the NIE. Okay, so the IE, what do we do with copper metal? Leave it alone or ionize it? Yeah, we leave it alone. We only ionize strong acids and soluble salts. This is neither of those. So we just leave it alone. Do I put a charge here? Should I put a 2+ charge on this? Or just leave it at 0? Leave it at 0. It's copper metal. Copper metal doesn't have a charge. Okay, silver nitrate. I didn't balance this. Do you see the atoms are balanced? Or no, the atoms aren't balanced. I need 2 silver nitrates and I got 2 silvers here. Now it's balanced. Silver nitrate. All nitrates are soluble. And so this is going to ionize to 2 silver ions plus 2 nitrates. Nitrate's also soluble, so this is going to ionize to copper 2 plus 2 nitrates. And silver is just the silver metal, no charge. Okay, the spectator is indeed nitrate. However, if there was acid present, and it doesn't matter the source of acid, any acid you could add to this would have changed this, the outcome of this reaction. But the nitrates are spectators in this particular case and don't participate. And so in other words, the silver ions oxidize the copper. The nitrates didn't play any role in this. You can see that from the net ionic equation. All right, next reaction is copper with hydrochloric acid. So we'll take some copper and hydrochloric acid. And what do we expect to form here?
Mr. Chabal, you skip zinc nitrate? Is that on purpose?
No. That wasn't on purpose. I'll come back to zinc nitrate. Okay, so copper and hydrochloric acid is going to make what? Copper 1 or copper 2 chloride? Copper 2 chloride. Chloride's not an oxidizer. Chloride's a reducer. So the only oxidizer is H plus and water. H plus is going to be better. So single replacement will work here. And hydrogen gas. All right, then we could check copper versus hydrogen activity series. And we can see that hydrogen is more active than copper. So we're going from less active, which is more stable, to more active, which is less stable. In other words, we're going from a weaker reducing agent, copper, to a stronger reducing agent, hydrogen. So the driving force is actually the reverse. So in the forward direction, we expect NR, no reaction. And so we don't expect copper to be oxidized by the H plus in hydrochloric acid. However, you might observe a reaction, but the reaction that you observe is different because copper, copper loses its luster. You might have a shiny, have you seen a brand new penny? They're really shiny and lustrous, but what happens with time? They start to get dull and they turn brown. The brown color is due to surface oxidation, which results in copper 1 oxide. So in this case, we can form copper 1 oxide, which is brown. But the HCl will react with this, but not in a redox reaction. The HCl will react with this in a double replacement reaction. What forms here in this double replacement reaction? Copper, in this case, is going to be copper 1 chloride. So we start off with copper 1 oxide. We're going to end up with copper 1 chloride and water. So we'll need 2 HCl's to do this. We'll form 2 copper 1 chlorides. And that should work.
Copper 1 want to go to copper 2?
Eventually. And so here the driving force would be stronger acid to weaker acid. It could, copper 1 could go direct. The copper that is, when it's oxidized, it can go all the way to copper 2 oxide. Copper 2 oxide is black. So if you heat up, have you ever heated up a copper penny in the flame? It immediately turns black. And so you don't really even see this brown.
Chem 4.
Yeah. And so if we take copper 2 oxide, this is also a double replacement reaction. We can take 2 HCl's. What's this going to form? It's going to form copper 2 chloride, which is aqueous like this, and water. So what acid could do is it could eat away the oxide coating. And so you can make an old penny look new, basically, because the acid will attack the oxide coating, but it won't attack the underlying metal here. So you'll have a shiny shiny metal penny after the acid. And so this is a side reaction that occurs here, not a redox, but a double replacement or acid-base type reaction. All right, and then I skipped one, copper metal and zinc nitrate. So let's take a look at that one over here. Copper metal plus zinc nitrate. What's going to form from this? What's going to form is copper 2 nitrate and zinc metal. Okay, again, there's no acid. This is under acidic conditions, so single replacement should work here. And we can compare copper and zinc. Pennies consist mostly of zinc. Did you know that? But they don't make them 100% zinc. That would save a lot of money. They don't make them 100% zinc. Why? Because zinc is really active compared to copper.
Mix it with nickel.
Yeah, the zinc corrodes quite rapidly. In other words, zinc is much more active than copper. So they have a zinc and then they coat it with copper or plate it with copper. And the copper is there to protect it, but traditionally pennies have been made out of copper. The amount of copper they use is worth more than a penny. And so there's been talk about changing it.
Yeah, they're going to do away with pennies altogether.
Yeah.
It's much more, costs much more to produce them.
So yeah, eventually they'll maybe do away with pennies. So zinc is a much stronger reducing agent than copper. You can see it here. Zinc is actually quite good. Aluminum is easy to oxidize. Zinc too. Iron. So here's zinc, and then copper is up here. So zinc is much more active. And so we expect no reaction here. The driving force is actually in the reverse direction. So we should expect no reaction in the forward. Okay, then we're going to look at zinc metal. So we'll get a piece of zinc and then test that with different solutions and single replacement reactions. Again, we're skipping the lead, so we're going to go with zinc solid with copper 2 sulfate.
Going back to copper and silver, but which acid can you use to test for silver? I think there's an acid, right?
Yeah. Test silver, you could use hydrochloric acid.
Yeah, there we go, hydrochloric acid.
Hydrochloric acid will not react with silver. So zinc and copper 2 sulfate will make what? Will make zinc sulfate, zinc's fixed charge at +2, and copper metal. Who's the oxidizer here? This particular case. Zinc is the reducer, and who's the oxidizer? Oxidizer takes electrons, so copper 2 took electrons to form copper 0, copper metal. This. Even if we had acid, we expect the same, because sulfate is an oxidizer too. In this case, sulfate's a spectator. But even if we had acid present here, copper 2 would still win because copper 2 is a stronger oxidizer than sulfate and acid. But here, we don't have any acid, so that's going to drop sulfate's ranking way down here. So there's going to be no test. But anyway, let's compare zinc and copper. Zinc is more active. Actually, we'll just use reducing agent. Zinc is a stronger reducing agent. Copper is a weaker reducing agent. There's less writing here. And so we expect reaction. There's a driving force. And therefore, I'm going to write the ionic equation. Copper 2 sulfate. Sulfates are soluble, except for silver, lead, mercury, calcium, strontium, barium. And so zinc sulfate soluble as well. So that's going to ionize. And then we have copper metal. Okay. And so over here in the net ionic equation, zinc solid is oxidized by the copper 2 ions. And this is going to make zinc ions and copper metal.
What metal is in stainless steel?
Mostly iron.
Iron?
Yeah, but other ones, nickel, some other stuff too, chromium. There are lots of different formulations of stainless steel. Many, many different formulations. And so they're all slightly different mixtures with a lot of the same ingredients. Okay, we're skipping the lead. Now we're going to go to zinc and silver nitrate. This should form what?
Zinc nitrate,
Zinc nitrate
silver metal.
and silver metal. And so again, we're going from a stronger reducer, zinc, to a weaker reducer, silver. And then we balance this 2 and 2 over here. And so the ionic equation will be zinc solid plus all nitrate salts are soluble. So we'll get 2 silver ions, 2 nitrate. Then nitrate salts soluble. And yield Zn2 plus 2 nitrates and 2 silvers. So overall, the zinc was oxidized by the silver ions. Silver ions are good oxidizers to form Zn2 plus silver metal. And then we have zinc metal and HCl. It's 2 silvers. So zinc metal plus HCl. What should this produce? Zinc chloride and hydrogen gas. We'll need, zinc versus hydrogen. Which one? I have zinc here, hydrogen up here. So zinc is a stronger reducer. So we're going from stronger reducer to weaker reducer, and therefore there's a driving force. Okay. And so let's go ahead and look at the ionic equation. I'm going to need 2 HCl's to balance it. So I'll have 2H plus 2 chlorides. We yield to Zn2 plus 2 chlorides plus hydrogen gas. And so net, the zinc was oxidized by the H plus. It's mineral acid, and it's going to form Zn2 plus and hydrogen gas. Somebody asked if they could test the hydrogen gas with a match, and they did, and it popped this morning. You could do that if you want, like Chem 4. This is the same reaction as in Chem 4. Okay, part 2. We're going to look at the halogens and the halides. Part 2A, control samples. What we're doing in part 2A is something called solvent extraction. So for example, we'll take a test tube, and this test tube is going to have chlorine water. That is Cl2 aqueous. Now, chlorine, is it polar or non-polar? You know? Chlorine is non-polar. Water is polar. So chlorine and water, they don't really like each other, but you still can dissolve chlorine in water. It's not 100% insoluble. It's like oxygen. Oxygen and water don't really like each other. Most of the oxygen will bubble out. But still, there'll be some oxygen dissolved in water. Otherwise, the fishes wouldn't survive. Well, chlorine, we can do that, and it turns out this is yellow. In solvent extraction, we're going to add a few drops of chloroform, CHCl3 liquid. Chloroform is a CCl, clear colorless liquid, and it's fairly non-polar. You'd predict it's polar, but it isn't that polar. It's more non-polar than polar. And one other thing, the density of chloroform is greater than the density of water. Most oils, most non-polar things float on the surface of water. But if you mix chloroform and water, the chloroform sinks to the bottom. It doesn't like water. And so what's going to happen is it's going to form a little bubble of liquid chloroform at the bottom here. And so what we want to do is we want to form a little pocket of chloroform, liquid, at the bottom of our test tube here. And the chlorine is right now in the water. And so what we're going to do is we're going to stopper this. and then make sure you got a tight-fitting stopper and seal it tightly. And then we're going to shake it up. Have you ever shaken up oil and water? What happens is you make an emulsion. And what emulsion is you have tiny droplets of oil dispersed in the water. So we're going to shake this up and make an emulsion. And hopefully what that does is it brings the little droplets of water in contact with chlorine molecules and extracts them out of the water phase. And so what we want to do is this. We want to shake, and then we want to transfer the chlorine from the water layer into the chloroform layer. And so what we're going to do is we're going to concentrate the chlorine down here in the chloroform. Now we aren't going to be able to get 100% of the chlorine out of here. So there'll still be a little bit of chlorine left up here. But as long as we get a lot of chlorine in the chloroform layer, that's going to concentrate it and it's going to brighten the color. Because we can't dissolve that much chlorine in the water. Actually, we can. It'll look yellow. But what we should see here is this should be bright yellow. So this is what we're doing. We're taking chlorine from the aqueous layer and extracting it into the chloroform layer. So I'll just represent it like this. Chlorine is moving from the aqueous layer into the chloroform layer. Once it hits the chloroform layer, it should brighten up like this. Now you have to be very careful because sometimes people shake this and the stopper comes off and then they get a whole bunch of chlorine water and chloroform all over their hands and arms. You don't want that to happen. But if you do get some on you, you'll want to wash it off with plenty of soap and water. It's not good for you. Even though they use chloroform as a general anesthetic. So we're going to do this the same with bromine. You know, if we take bromine water, which is kind of a rust color, red-orange color, and we concentrate that into a chloroform layer, this should come out bright orange. In iodine, we're going to extract that too in another test tube to make iodine in chloroform. This should be a dark purple. So our controls are just, all we want to do is we want to look at what those halogens look like in chloroform. Okay, then we're going to do reactions. And so let's look at part B. So part A is solvent extraction. And again, be careful here. Especially you don't want to use too much chloroform. You know, it's somewhat volatile, it can create pressure. So sometimes they release the pressure by twisting the stopper a little bit to release pressure. And so you should hear a little sound. All right, so part B, let's take a look at the reactions that we're doing. The first reaction is we're going to take the chlorine and KBr. So we're going to take chlorine, Cl2, plus KBr. This looks like a single replacement, and it is, but it follows a different pattern. And you can learn the pattern, or we can skip it. Probably we'll just skip it. We'll use the chart method because in the single replacement patterns, A plus Bx. A is the reducer. Is chlorine a good reducer? Not at all. Chlorine's a strong oxidizer. So A plus B. B is the oxidizer, potassium ions. Are potassium ions good oxidizer? No, potassium ions are one of the worst oxidizers on the chart. And then X, bromide. Well, it's all mixed up. And so what we do is we use the chart method. And so we're going to have chlorine, we're going to have potassium ions, bromide ions, and one more. What's one more? And water. And then we list it. Chlorine's a great oxidizer. Potassium ions, one of the worst oxidizers on the chart. Bromide is a decent reducer, Water is both an oxidizer and a reducer. And then from the chart, we pick the strongest. The strongest oxidizer is chlorine. And then bromide versus water, bromide wins. Here. And so the reaction should be between chlorine and bromide. Let's take a look at that. We're here. So chlorine can pick up 2 electrons to form 2 chlorides. And bromide, 2 bromides can go to bromine plus 2 electrons. And then we just combine these two. And so we get chlorine reacting with 2 bromides to produce 2 chlorides and bromine. And then we compare. We can compare this using the activity series, or we can just analyze it directly. Here. And that is, chlorine picks up electrons. So that's the oxidizer. This is the conjugate reducer. This is the reducer. It's losing, and bromine would be its conjugate oxidizer. And so chlorine's the oxidizer, bromide's the reducer, and then chloride is the reducer, bromine is the oxidizer if we went backward. Now let's compare the 2 oxidizers. Chlorine versus bromine. Which one is it? Which one's stronger, chlorine or bromine? Well, the chart we know goes fluorine, chlorine, bromine, and then iodine. So in this case, chlorine's stronger than bromine. And so this is activity in terms of oxidizer. Chlorine's more active. It's closer to fluorine than bromine. And that means the reducers must be the same, and therefore this has driving force. If this has driving force, then what we're going to form is bromine aqueous. And the way we're going to detect if a reaction occurs is we're going to add chloroform to this reaction mixture, and we're going to try to extract our product, bromine, out from the water phase into the chloroform phase. And so we're going to add chloroform to this, stopper it. You should use a rubber stopper. Don't use natural cork, because the natural cork has little pores in it, so it doesn't seal as well. And then we're looking for what color in the chloroform. We hope to see bright orange. If there's no reaction here, then we're left with chlorine, and we'd see bright yellow instead of bright orange if there's no reaction. Right? But since there is a reaction here, we expect to see bright orange in the chloroform layer. Okay, does that make sense for that? The next reaction is chlorine plus potassium iodide. Is chlorine powerful enough to oxidize iodide? Yes, because what would you form? You'd form chloride and iodine. And so again, we're going from stronger oxidizer, chlorine, to weaker oxidizer, iodine. So the next reaction would be fine. And then we have, let me take a look at this next one here, bromine and KCl. Actually, I don't have much time. I'll skip this one. I mean, but you guys can do it, and then you can follow the same pattern for these reactions in the C. So I'll leave the remaining reactions for you to figure out. I want to go to part C here. Halides as reducing agents. And so we'll take a look at C1. C1, FeCl3 and KBr. FeCl3 plus KBr. FeCl3 and KBr yields NR for metathesis. And therefore we look for redox next. This is not acid-base. And so there's no reaction for acid-base either. But going to redox, we do this using the chart method. We're going to have iron 3, chloride, potassium ions, and bromide ions, and water. Iron 3 is a pretty decent oxidizer. Chloride is a reducer, pretty poor one. Potassium ions are a very poor oxidizer. Bromide is a decent reducer. Water is both an oxidizer and reducer, but not very good at any of those. And so the oxidizer here is going to be iron 3. The reducer, the best one, is going to be bromide. And so we copy the reactions off the chart. Looking at the chart, iron 3 can gain 1 electron to form iron 2. And then 2 bromides can go to bromine plus 2 electrons. Okay, so what I'll do is I'll multiply the top reaction by 2 and then combine these. And so what I'm going to get up with is 2 iron 3 plus 2 electrons plus 2 bromides is going to yield 2 iron 2s plus bromine plus 2 electrons. So the 2 electrons cancel. And then here, if it's gaining electrons, this is an oxidizer. This would be its conjugate reducer. If it's losing electrons, this is a reducer. This is going to be its conjugate oxidizer. So this is our OA. This is our RA. This would be our RA in the reverse. This would be our OA in the reverse. So we're going to compare iron 3 versus bromine. Which one is stronger? So I have iron 3 here, and then I look for bromine. Let's see it. Yeah, up here. So iron 3 and bromine. Which one's stronger? Bromine. So this is stronger, this is weaker. And that means the reducing agents have to follow. This has got to be weaker, this has got to be stronger. And therefore the downhill direction is backwards, and therefore we expect no reaction. So we don't expect any reaction. We don't expect to form any bromine in this case. One way we can analyze this to show that there's no reaction is we could try to extract bromine. But, we're not going to extract anything. Bromine didn't form. Okay, the next reaction here is with Ki. So what we're going to do next is we're going to look at iron, iron nitrate? No, iron chloride. Iron 3 chloride plus Ki. Here again, there's NR for metathesis. And these are neither Bronsted acids or bases, so we're going to look at redox. And basically, it's going to be the same kind of pattern here. It's going to be, in this case, we're going to have iron 3. This is going to be our strongest oxidizer. And iodide. Iodide is an even better reducer than bromide. It's bigger. And so this is going to be our reducing agent, etc. And so we're going to pick these two. And then we're going to get the similar reaction. I'm just going to skip some steps since I'm out of time here. Iron 3 plus 2 iron 3s plus 2 iodides. This is going to produce 2 iron 2s plus iodine. And then we compare the oxidizers. Iron 3 is an oxidizer, iodine is an oxidizer. And then let's see where this lies. Here's iron 3, here's iodine. Iron 3 is stronger, iodine's weaker. So this is going from stronger to weaker. Therefore, there's a driving force here that's present. And to verify this, we're going to take our iodine that's going to be formed here and extract that using chloroform to make this, the dark purple layer of iodine and chloroform. Is that okay? There? So here we're going to do solvent extraction to detect the presence of iodine. C2 we need a hot water bath for this. There's going to be hot plates set up in the hood. You can turn those on and put a beaker half filled with water to serve as your hot water bath there. You can do that early to let it warm up. But in this particular reaction, we're going to take some solid potassium permanganate. And that's highly concentrated. It's pure potassium permanganate, not an aqueous potassium permanganate, which would be a mixture. And then we're going to react this with HCl. Here, there could be a potential metathesis reaction. The potential metathesis reaction could form permanganic acid and KCl. There's a driving force for that. But this is not a lab on metathesis or acid-base. This is a lab on redox. And so we're going to look at the redox reaction that might occur here. And so again, this is going to be a chart method. Potassium ions, permanganate, H+, chloride, and water. And then potassium ions are an oxidizer, permanganate's an oxidizer if we have what present? Permanganate is an oxidizer if there's what present? Acid. You know, permanganate and acid, there's got to be H+ present, and there is H+ present here. And so permanganate and acid is an oxidizer. Acid alone is also an oxidizer, but not as strong. So if we look at H+ alone, it's not nearly as effective. And then chloride is a reducer. Water is both an oxidizer and a reducer. So which one's the strongest oxidizer? Potassium ions? No. Water? No. H+? No. Permanganate and H+? Yes. So that's our strongest oxidizer. What's our strongest reducer? We only have two, chloride versus water. So if I look at chloride here versus water here, which one's stronger? Water is stronger. I'm going to dot this. Did I talk about this the other day? I don't think so, to this class. Chloride, water is stronger, but chloride is easier to oxidize. Is chloride, you just pull an electron off the outermost shell. And whereas water, you have to rearrange things. You know, water, you have to pluck the electrons off oxygen, which means breaking the bonds and doing a bunch of other stuff. So easier to oxidize means you aren't going to get as big of a return energetically. So this is like this. Let's say you're going to invest $100. And you're going to invest this $100, you're going to get some interest. Situation is this. You could have, let's say you could have $4 of interest tomorrow for that $100. Or you could have $5 of interest next year. What would you rather do? Have $4 now or wait 1 year and take $5? Well, you should probably wait 1 year and take $5. But what do you think you'll probably do? Just take $4 now, and then you have to wait 1 year, right? And so that's kind of like nature here. This happens a lot faster, but you know, if you wait, then this is going to lead to more stability. But this is the only exception. This is what we call kinetics, and I'll talk more about that later. And so this is an exception. That is, water is a more powerful reducer than chloride, but chloride is reduced before water. So what we're going to have is we just copy the equation off the chart. Manganate permanganate requires how many hydrogens? 8. You know, we have 4 oxygens. Plus 5 electrons. This is going to yield Mn2 plus 4 water. Okay, that's one reaction. The other reaction is chloride. So we're going to have 2 chlorides. This is going to produce chlorine plus 2 electrons. Okay, I'm going to multiply the top one by 2, and then the bottom one by 5. And so I'm going to get 2 permanganates plus 16H plus 10 electrons plus 10 chlorides. This is going to produce 2 manganese 2s plus 8 H2O plus 5 chlorines plus 10 electrons. Okay, then let's simplify. The 10 electrons cancel, and then looks like that's it. So I'm going to end up with 2 permanganates plus 16H plus 10 chlorides yields 2 manganese 2 plus 8 H2O liquids plus 5 chlorine gas. Okay, is there driving force for this? So this is our oxidizer in the forward. In the reverse, this would be our reducer. This is our reducer in the forward. This would be our oxidizer in the reverse, the conjugates. And so we're going to compare permanganate and acid versus chlorine. Which one's a stronger oxidizer? Permanganate in acid or chlorine? Permanganate in acid is stronger than chlorine. So this is going from stronger to weaker. Okay, here we aren't going to do the solvent extraction. What we're going to see is we're going to see chlorine gas come off. Chlorine gas is a yellow-green gas. And so you should see some effervescence or something. Yellow, green, gas. Do it in the hood, because you don't want to inhale the chlorine. Okay, 2 more here. Copper and bromine. So we're going to take, this time we're not going to use the plate, we're going to use the wire. And we're just going to get a little bit of wire. You don't need much, like a quarter or less, like 1/8 of a test tube. And then we're going to mix this with bromine, aqueous, and water. Water is very reactive, so the reaction is going to be between copper and bromine. And so what can happen is copper can lose 2 electrons, bromine can gain it. So copper loses 2 electrons, will form copper 2 plus, and bromine gains those, will form 2 bromides like this. Okay, one thing is this is blue, but it's hard to see, and this is colorless. This is kind of a brown-orange. And so what you want to see is, it says to look for the blue. You aren't going to see the blue because it's too faint. What you should look for is, you should look for the brown color of bromine to disappear. And this is going to be almost colorless over here. So when you see the brown color disappear, that's enough. You can stop there. Because what we're going to do is we're going to analyze the product here. So we're going to have product. This product is going to contain copper 2 and bromide. The test for copper 2 is this. We'll take our copper 2 and mix it with aqueous ammonia. And so that's 2 ammonias and 2 waters. And this is going to form copper 2 hydroxide, solid, plus ammoniums, 2 ammoniums. This is a light blue precipitate. And so a blue PPT. You might see this blue PPT, but what's going to happen is this. If we keep adding ammonia, this PPT disappears. And so if we add excess ammonia, what's going to happen is we're going to form this. And this is called tetramine copper 2. This is a dark blue solution. Dark blue solution. So what I need to do is I need to divide the product in half. So this is going to be copper 2 and bromide. And so I'm going to put half of the solution in one test tube and the other half in another test tube. In the other test tube, I'm going to test for bromide. I can't do both tests in the same test tube because it's just going to make a mess. So again, I'll take the product, divide it into two test tubes. And so this is going to contain copper too, but we're just going to test this for bromide. For bromide, we add silver ions. Silver ions, like bromide, we're going to precipitate silver bromide, which is a precipitate. So we should see a white, off-white, yellow precipitate of silver bromide. This is a confirmatory test. And then the final reaction here is silver plus iron 2 ions. We've been using iron 3 so far, but we're going to use iron 2 sulfate for this, ferrous sulfate. This is green, and it's aqueous. And then we're going to add silver nitrate to this. And this is going to be a little bit complicated because two reactions occur. One is the metathesis reaction. Metathesis reaction precipitates out silver sulfate, solid, and we're going to be left with iron 3 nitrate, or iron 2 nitrate, sorry, iron 2 nitrate, like that. So we have driving force for metathesis, precipitation. But eventually we're going to have some redox occur too. And the redox is going to be, well, what do we have? We have iron 2, we have sulfate, we have silver ions, we have nitrate ions, and we have water. Now if you read the chart once in a while, you'll see that iron 2 is both an oxidizer and a reducer. It occurs on both sides of the chart. Sulfate is an oxidizer, but what's it missing? Sulfate is missing acid. There's no acid in this mixture, so it's missing H+. So we could ignore it. Ignore it because its rank is going to be much lower. Silver ion is an oxidizer. Nitrate is an oxidizer, but it's missing what? It's missing H+. So we ignore this one too. And then water is both an oxidizer and a reducer. And so the strongest oxidizer is silver ions. Silver ions are good oxidizers. And interestingly enough, the strongest reducer is iron 2. And so the reaction that we're going to have here is iron 2 is going to get oxidized. That is, it's going to lose electrons. It's just going to lose one electron to go to iron 3 plus an electron. And then silver ions will gain an electron to make silver metal. And so we're going to just add these. The electrons cancel. And so what we end up with is iron 2 plus Ag plus is going to yield iron 3 plus Ag solid. Initially, it looks black, this precipitate, but with time the crystals grow bigger and look silver. Metallic silver color. Okay, are there any questions? Uh-huh.
I'm kind of confused. So part A, when we use the core form, do we extract that and use it for part B?
No, the control is just you leave that there for colors.
Oh.
And so when you do part B of that, then you'll see when you do the reactions what it is. Is it chlorine, bromine, or iodine?
So is there any point where we have to extract something from the reaction, or is it?
It is. You mix chlorine water with KBr, shake it up, and then extract it. Actually, you're going to mix chlorine water, KBr, and chloroform. So you'll put in a few drops of chloroform in the reaction and then shake it up and see what happens. And so that's just extracting. If there's a product that forms there, and there is, you'll see what it is in the chloroform layer. Is that okay? Other questions? So you're going to work with a partner or alone? If you work with a partner, I want both of you to take down the observations. I don't want you to divide the work in half, like your partner does one half of the experiment and you do the other half of the experiment. That's not going to work. So both of you just work together and take observations of each reaction so that that you see it, see what happens. Okay, well that's it. Go ahead and get started. You'll need safety goggles for this lab.